Geez, that bowling ball is pretty precarious there. It's gonna be coming in hot once I blow that hydrogen balloon. Does this setup give you a sense of impending doom? That's your intuition about potential energy kicking in. Today on Real Chem, we'll hone that intuition. Not just about gravitational potential, but about chemical potential. Let's find out what factors drive chemical reactions. That was hydrogen reacting with oxygen in the air to form water. The hydrogen and oxygen chemically moved downhill, just like the bowling ball rolled down the ramp. When hydrogen and oxygen moved down the chemical hill, they released a ton of heat in an exothermic reaction. The reaction is being driven by enthalpy. Let's take a look at another reaction. In this experiment, we're going to mix ammonium chloride and barium hydroxide. I'm going to pour some water on this wood so we can really see what's happening. I'm going to place this Erlenmeyer here, and I'm going to mix barium hydroxide and ammonium chloride. And stir. The mixture absorbs energy from the surroundings. In this case, it absorbs energy from the water, turning it to ice and freezing the beaker to this board. Sometimes. This is called an endothermic reaction. But wait, what causes this to happen? Why would a chemical reaction move up a chemical potential hill? What's driving this reaction? Because it's not enthalpy. Let's recap where we're at. In the first demonstration, the reactants moved and formed lower energy products. In the second demonstration, reactants formed higher energy products. So energy isn't the whole story when it comes to driving chemical reactions. What else is there? To answer this question, let's take a close look at processes where absolutely no energy is transferred. I offer you this thought experiment. Two people, two chairs, sitting in two fully insulated chambers. That means no heat exchange. Therefore, the system's energy can't go up or down. Our two people are separated by only one small dividing door. It's a pretty calm day, but then one person, let's say chamber 2, lets loose. At that precise moment, the dividing door slides open. Now, I think most of us have a pretty good honed intuition on what happens next. The gas spreads out through the entire space of the chamber. And the person over here, well, they get hit with a large dose of smelly molecules. But why? The system isn't rolling down an energy hill. It's fully insulated. This isn't about energy. It's because there are more ways for these molecules to spread out through the chambers than there is to stay clumped over where they started. The driving force that comes from those increased ways of ordering the smell molecules is called entropy, the natural tendency towards the spreading out of matter and energy. To figure out whether a reaction can happen thermodynamically, we combine these ideas. Energy changes, enthalpy, and large numbers of arrangements, or entropy. Enter Gibbs free energy. Delta G is Gibbs free energy change. Delta H is the enthalpy change in the reaction. This is mostly due to bonding. Delta S is the change in entropy. This is the number of ways of arranging the system. And T is the absolute temperature, because entropy's effect depends on it. Here's what we've learned. Reactions releasing energy tend to happen. Reactions that increase entropy tend to occur because they create more possible arrangements, making higher entropy states more probable. Let's look at them together to see how our endothermic reaction worked. For a reaction to be spontaneous, delta G must be negative. It's the real hill. In this reaction, our enthalpy change is positive. That's bad for delta G. But we make a bunch of ammonia gas. So we spread out matter, which means delta S is positive, and that's good for delta G as long as our temperature is high enough. So there you have it, enthalpy and entropy. Some reactions roll downhill, giving off energy. Some just spread out because they have to. Other times, the spread out is so great that the reactions can be driven up to pull energy and go uphill. That's real chem.